I'm especially excited to be talking with people at a Southern Baptist seminary. I grew up Southern Baptist. I grew up in the South, and my mother's father was a Southern Baptist preacher. He's gone on to be with the Lord now. And so I having grown up in Southern Baptist churches and being in one now, I'm excited to be here with you today virtually. And so what I want to talk with you about today is some recent developments in my field and how we think more broadly about the philosophy of science in my field. And these are getting into sort of broad and big questions that bear on issues that I hope will be of interest to you, issues such as what it means to be human and philosophy of mind and philosophy of theology. So I'm going to start very firmly in my field of physics, and I will try to alert you when I start to move out of it and into philosophy. So the big ideas that I want to get out on the table are reductionism and emergence, and how does that ultimately bear on freedom? Are we stuck, in the laws of physics, or do we have real freedom? And what are the implications of that? So the first big idea I want us to think about is, what is it that makes a physical law fundamental? How do we know when we've found the deepest and truest things about the universe? That's what physicists want to do. We want to find out how the world works, and we're ultimately wanting to find that big equation that will tell us everything. Sometimes people call that the theory of everything. How do we know we're finding the deepest and truest things out about the universe? For a long time, scientists worked under a framework of reductionism, and it goes something like this. It basically says, I will find out the deepest and truest and most fundamental things about the universe by breaking things into bits. And I'm going to be honest, this is why a lot of us go into physics, okay? As kids, we were the kids who were breaking things, right? Okay, so why? Because we wanted to find out how they work, right? So this looked like we take a hunk of matter and we break it into its bits, and we found that there are atoms inside, but we didn't stop there, okay? We took the atom, built really big, expensive machines with taxpayer money, thank you, and smashed the atoms together, and we found out what's inside of the atoms, and we found electrons and protons and neutrons, and try as we might, no one's been able to break apart an electron yet, although we still try. But when we take the nucleus of the atom, what's in the middle is the protons and neutrons, and you smash those things to bits, you find that the protons and the neutrons themselves are made up of other particles called quarks. And so this is basically how reductionism tells you to go about finding the deepest and truest things in the universe. It says, okay, I'm going to break things up into their tiniest bits. I'm going to understand everything I can about the bits, and then I ought to be able to reconstruct things back up. Now, implicit in this way of thinking about things is that it means you're going to come up with a hierarchy of descriptions and a hierarchy of disciplines that are looking at the natural world. And so it might have an organization that looks a little bit like this, okay? At the very bottom where we were just talking, we had broken apart matter into atoms, and then those atoms into quarks and leptons. Those are other names for leptons are another name for electrons. You can break those apart, we think, and find strings. That's not confirmed, but there's a lot of thought that could be the case. But then the way you would want to think about things is, okay, I understand the strings. Let's build the electrons, protons, and neutrons out of them. We'll build the atoms out of them. We'll build the molecules out of them. We'll get lots of them together and build materials. That's many-body physics. We'll get lots of the atoms together and build big molecules and head towards molecular biology and towards cell biology and on up the chain, okay? So you can read more about this, by the way, in Phil Anderson's famous article, More is Different. It's actually available for free from Science magazine. So this would be one way of going about trying to find the deepest and truest things about our universe. Ultimately, though, reductionism is looking at everything from a deterministic point of view, right? It's basically saying, okay, I've broken matter up into the atoms. I can break the atoms up into their constituent bits, but I'm looking for the laws that the little particles obey. Laws like electricity, magnetism, gravity. And so once we do that, here's what that leads to. It basically says, look, if we know the positions and the velocities of all of the particles in the universe, I've said atoms here, but let's speak more broadly and say particles, because not everything's in an atom. If we know all of that, you give me an instant in time where I know the exact position of every particle in the universe, and I know its exact velocity, then I should be able to turn the crank on all of these equations, and I can predict their future exactly. Everything is determined. That is, it's the idea that physical objects follow physical law. Now, if you go so far as to say, well, that's all there is, we can always take any system and understand it by reducing it to its smallest bits, and then describe that large system again by how the little bits interact. If you take that to its extreme, then you get some rather extreme conclusions about what it means to be human. And of course, you can start to ask, larger questions like consciousness. Consciousness and philosophy of mind is out of my area of research. I really enjoyed reading, though, Susan Blackmore's book. She went and interviewed a lot of people working on the area of consciousness. And this is a highly interdisciplinary field, as you know. It involves theologians, it involves philosophers, neuroscientists, doctors, and so forth. And so she interviewed this set of people. And interestingly, because she's implicitly working from a reductionist mindset, because she's implicitly working from an assumption that the material world is all there is, and whatever I see in the material world can be reduced to these fundamental bits, then she comes up with a rather dramatic conclusion that free will must be an illusion. I mean, she actually writes this. She writes, along the lines in the introduction to her book of I know I'm not really conscious and it's an illusion. And that's rather, well, interesting, a little bit scary, but there it is. I think it's very honest though, right? If you really are looking just from a materialistic point of view, where physical objects follow physical laws, and all there is are physical objects that follow physical laws. Laws are laws, they're not suggestions. And so these things just do what they're supposed to do. There's no freedom there. So people have thought about maybe some ways around this, because I don't know about you, but I have the experience that I believe I have some freedom. Now, of course, as believers, we have, of course, the theological ideas and the teachings of Christianity that we really do have freedom, and this is a gift from God. But as far as people who are thinking from that materialistic point of view, there are a couple of ideas that have been put forth for how to get around this seeming, lockstep. What does the reductionist mindset tell you for how things should operate? Is there ever going to be any freedom? So one idea people have come up with is maybe quantum will save us. Maybe we will be able to recover some level of freedom at large scale system sizes, right? Large scale being us humans or larger. Maybe quantum gives me that little bit of wiggle room to where I can have some freedom. So there's actually a couple of problems with that. One problem is that the individual events in quantum mechanics, they're probabilistic. That is, let me be careful, we describe them with probabilities. We actually don't yet know whether those probabilities are inherent to how the particle operates, or whether those probabilities are a proxy for our lack of knowledge. That's an open question. However, suffice it to say that we model it using probabilities. So, if that really is inherent to the universe, if there really are actual, truly probabilistic events, maybe that leaves you the little bit of freedom in which our free will can ride. But, chance is still chance, right? So random chance really isn't me choosing, right? I mean, I don't know about you, but I have this impression that when I walk into an ice cream store and I am debating whether I should get triple chocolate chunk brownie or pumpkin ice cream with gingerbread bits in it, I'm making a real choice out of freedom. And random chance, thinking that impression comes from random quantum events, isn't actually choice, right? It's less control. It's not more control. And then there's another problem with thinking that quantum indeterminacy might come to the rescue for us. The other problem is that large-scale objects actually become deterministic again, even under the assumption that quantum events are probabilistic. If you've ever thought about, well, how is it that casinos make money? Maybe you don't think about this, but casinos actually make money off of seemingly random events, right? People are throwing dice or shuffling cards or whatever. They look like random events to us, but they play the game enough times and they know the outcome of enough throws of dice, right? They know that if enough people every day play their games, they know exactly what profit margin they expect to make. So that's just a way of thinking about how several probabilistic events added up can give you, at the end of the day, a large event that you can predict with great precision. So large scale objects still follow this determinism of, we know what the physical laws are, they obey the physical laws in lockstep. So quantum won't get us out of this dilemma. But another thing that's been put forth is emergence. Maybe the big idea of emergence could come to the rescue. So here I'm going to quote Bill Newsom, who's a professor of neurobiology and the director of the Stanford Neurosciences Institute. And he had this to say about it. He said, "I suspect that answers will ultimately lie in a deeper understanding of emergent phenomena in complex systems." So this phrase here, emergent phenomena in complex systems, that is firmly in my field of physics, and goes beyond it to remember that hierarchy I said. It also goes up the hierarchy. I am in a discipline known as condensed matter physics. We mean condensed in the sense of condensation, like gas condenses to liquid, liquid condenses to solid. It's basically objects you can hold in your hand. If you could hold it in your hand like this rock, it's our domain. So we have very well-defined tools for talking about emergence and what it means. By the way, I should alert this audience that Bill Newsom is a believer. So if you're interested in reading from the perspective of a believer who's active in the field of neurosciences, I recommend his writings. So one of the issues to think about in regards to emergence and reductionism, things like that, is that this big idea of reductionism, where I'm going to understand large scale things by breaking them into their bits and into their bits and into their bits, is that reductionism, while it has helped us answer a lot of important questions about how the universe works, it doesn't give us the ability to answer every question, okay? So reductionism fails to help us answer many important questions. So for example, I've got the Mona Lisa here, and the Mona Lisa painting is special in many ways, but she's smiling, and she's smiling in a kind of subtle way. She's smiling with her eyes. And if you wanted to ask the important question that art historians have asked for a long time, how did this happen? How do we get a painting where she's smiling in such a subtle way? Reductionism actually tells you how you would go about trying to answer that question. Why is the Mona Lisa smiling? How did this happen? The reductionist framework would tell you to do the following. It would say, okay, we're going to answer this question. Let's break it up into its bits, to which the art historians, throw themselves in front of the painting and prevent you from doing it. But let's just, take this thought experiment further. The reductionist would say, I can answer this question. Let me have some of that painting. I'm going to take the pigments off and do a chemical analysis of the pigments. And because I want to understand how the little bits work. And if I understand how the little bits work, then I should be able to understand everything and know everything. And you can see how that doesn't work here, right? We've got a question, why is the Mona Lisa smiling? But reductionism doesn't help you answer it. You need to be thinking at larger scales in order to even address the question. A chemical analysis of the pigments won't answer this question, okay? So there are some cases where reductionism just isn't a fruitful way to go about things. So enter my field of physics, condensed matter physics. This is a lovely photo of a drop of water, actually taken by my Uncle David. Photo used with permission. Thank you, Uncle David. So in condensed matter, we mean condensed in the sense of condensation, as in gas condenses to liquid, liquid condenses to solid. We study phases of matter and phase transitions. And you might think, aren't there just solid, liquid, gas? Shouldn't you guys be done? But there's way more than solid, liquid, gas. There's many, many, many phases of matter. And I actually study electronic phases of matter. I study phase transitions that electrons have inside of solids. And there's an infinite number of those. So we're not stopping anytime soon. But condensed matter, briefly, is stuff you can hold in your hands. If it's stuff you can touch, if you can hold it in your hand, it's our domain. An atom is too small. I can't hold just one atom. A star is too big. But something you can hold in your hand is a condensed matter object. So let's think about a question where reductionism might not be the most fruitful avenue, but condensed matter ideas like emergence might help. So we could ask the question, hey, why is this material hard? This is quartz. I like quartz. I used to find hunks of quartz in my backyard growing up in Alabama. And quartz is made of silicon dioxide. It's actually made of the same stuff as windows. So if you have a window around that's glass, they're just different phases of the same material. The glass is glass, but the silicon dioxide is crystal. You could ask the question, hey, why is this material hard? Okay, the reductionist answer, right? The reductionism point of view would say, well, break it into its bits and then I'll tell you what's going on. So you'd break it into its bits and you'd find out it's made of silicon and oxygen. Okay, so the reductionist mindset would say, okay, this material is hard because it's made of silicon dioxide, right? And that might seem like an okay answer until you start asking the question more broadly. So, thinking about quartz, if you ask the question, why is it hard? The reductionist answer would say, well, tell me what it's made of and I'll tell you why it's hard. But the problem with that is that this crystal on the right is also hard. This is bismuth. I really like bismuth. It's a very pretty crystal. So the reductionist answer would say, well, let me break it into its bits. I'll learn what the bits are, and then I'll tell you why it's hard. So the reductionist answer would be, this is hard because it's made of bismuth. But there must be something more here going on, right? We're really ultimately looking for the answer which has the broadest explanatory power, right? And so it's not quite right. And here I have some examples of my own. Why? Because I'm a condensed matter scientist and I like hunks of rock. So I have here some calcites and I have some fluorite here, and they're both hard. And so to say that this one's hard because it's got fluorine in it, and then to say, well, this one's hard because it's got calcium in it, there's something wrong, right, with that, because this is hard, but it doesn't have any calcium in it, and this one's hard, but it doesn't have any fluorine, and this bismuth crystal is hard, but it doesn't have any silicon in it. So the answer here doesn't lie in the constituents. There's something large scale going on. The larger scale explanation would simply say, look, they're in the crystalline phase. These are all crystals. My calcite's a crystal, my fluorite's a crystal. What's on the screen there, the quartz is a crystal. This is a crystal of bismuth. They're hard because they're crystalline. And that's the answer that would give you the broadest explanatory power. There's emergent behavior, we would say, at the large scale that comes in that you need to take into account. So that's one of the big ideas of emergence. Emergent phenomena are things that arise in collections of particles. So for example, right, this collection of atoms got together and became crystalline, and the emergent behavior is that it's hard, there's a rigidity to the thing. A wave is a great example of emergent phenomena, depending on the context of it. So if you're thinking about a wave on water, that's an emergent phenomenon, because the wave is actually something that's existing because of a collection of water molecules all doing the same thing, and that makes a wave. Maybe you've been in a baseball stadium and participated in doing the wave in a baseball stadium, and this is where the audience members stand up and sit down in synchrony, making a wave-like pattern. And The wave in that context is an example of emergent phenomena. So you wouldn't try to understand that wave by saying, oh, I can explain that wave because of the people. No, not quite. The wave is the wave. It's this emergent thing. It happened in the collective and at the collective scale, and it's a new object. You couldn't look at one person and say, oh, that one person's doing the wave. In fact, I know that from a rather unfortunate experience when I was in college. I was at a small school, and we didn't have big audiences at our sports events. It was Caltech, okay? So my friend and I decided to go watch the water polo team. We were the only two people on the Caltech side in the audience, and we decided, hey, let's do the wave. And let me tell you, you can imagine right now, that looked lame, right? Two people cannot do the wave. You need a whole crowd, right? So that behavior in a baseball stadium, or as we tried to do it in a water polo stands, that behavior is emergent, but you need the collective to do it, right? And you couldn't look at one person and say, oh, that's the wave. No, it's in the collective, okay? You have experience actually with lots of emergent phenomena, not just waves on water or waves of people, or right now you're hearing my voice through sound waves, right? The compressional waves in the air are carrying the sound. That's an emergent phenomenon, that wave right there. So lots of waves are emergent. Hardness in a material is an emergent phenomenon. Wetness is emergent. Governments are emergent. It's this question of, if you only ever met one human being, you know, let's say you were an alien race and you came to study us. If you only ever met one human being, would you predict presidential elections? You know, would you predict currencies, you know, and conversion rates between currencies? These are emergent phenomena that happen at the large scale. Wetness is a great example of an emergent phenomenon because, you know, water, when it's at room temperature, is wet. So, you know, I have here, for example, you know, a glass of ice water, and most of the water in here is liquid, but you can see the ice that's not. But the liquid part, right, is wet, right? If I stick my finger in here and stir it around, it's wet and it feels wet. But what if I gave you only one water molecule? If I gave you only one water molecule, would you say it was wet? You actually couldn't. In fact, wetness is a great example of emergence because you can't even define the concept with one molecule, right? The concept itself didn't have any meaning until you had a huge collection of molecules. This is about 10 to the 23 molecules, about a billion, million molecules. So you need a lot in order to get these emergent behaviors. So what does emergence teach us? Okay, so what are the lessons that we can take home from what we've learned about emergence? And again, I like starting from my field to think about emergence, partly because I'm in it, but I think we can provide a good foundation for thinking about the larger issues because in condensed matter physics, we have well-controlled methods for understanding the phenomena, not just experiments where we go in and test things in a lab, but we have well-controlled mathematical derivations of exactly what emergence means. So we have a well-defined handle on it. So here's what we learn about emergence. Here's what it can teach us that I think are take-home messages that can be ported outside the field. We learn that new entities arise at new levels. For example, that wave in the baseball stadium, that was a new phenomenon. It doesn't exist just at the single person level. New laws exist at new levels. For example, you know, wetness and how wetness behaves. These arise at new levels. So I would say that one lesson we can take home from emergence is to take high-level observations seriously. They are meaningful and they do teach us things that are important about how things work. Another thing we learn about from emergence is this idea that different microscopic situations can lead to the same macroscopic result. We saw it with the rocks, right? So this is fluorite and this is calcite, and they're both hard. So even though they have different constituents, they have different microscopic situations, it led to the same macroscopic situation, and that they're both hard, okay? So, and you know, liquids are similar, right? I have a liquid here of water, but you know, we could have other liquids like oil or alcohol, and they have the same large-scale behavior independent of the constituents that make them up. There's something new that arises at the large-scale situation. So reductionism in and of itself can't explain why these high-level behaviors occur. Reductionism isn't the answer to why did the wave happen in the baseball stadium. It's not the answer to why is the Mona Lisa smiling. And it's not the answer to why does water become wet when it's liquid at room temperature. And this also brings up the idea that causality itself, what is causing what? Causality can enter at higher levels than the microscopic, right? So for example, why are these water molecules sitting in this glass right now? It's for higher level reasons, right? There's a higher level reason, which is that I poured it into a glass, and now the glass is providing a container that controls it. So the causality here of why is this liquid right here, right now, came in through higher level causes, namely me pulling the glass out of the cabinet and filling it up. So causality can enter at higher levels, not just the microscopic. So again, reductionism, as I was arguing, fails to answer certain kinds of important questions. And so you might ask, well, is emergence always going to be a better strategy? It is in some cases, all right? But I'm skeptical that it will answer all the questions we want to answer about consciousness. You know, so as Bill was saying, I suspect that answers, and he means to consciousness and free will, answers will ultimately lie in a deeper understanding of emergent phenomena in complex systems. I personally am skeptical about that. So now here's where I'm going to not just wear my physicist hat, but just go a little bit into a philosophy of science as well. So here's some of the issues I have with that. The known examples we have of emergence, the ones where we know what's going on, we can track them experimentally in a lab, and we can put hardcore mathematics behind what's going on. All of those examples are still deterministic, right? I mean, this water is still, you know, is wet. It's always going to be wet under these circumstances, right? This is actually ice temperature water, but room temperature water is always wet every single time. It's deterministic. It always does what it does. Crystal and silicon dioxide is always hard, right? You know, this fluoride, when it's in its crystal phase, is always hard. So even under emergence, at least as it comes up in condensed matter physics, it's still completely deterministic. And determinism isn't freedom. We're not going to get freedom and the ability to account for how it is that I choose between the triple chocolate brownie chunk ice cream and the pumpkin ice cream with a ginger snap in it, because half the time I choose one and half the time I choose the other. They're so good. So determinism really isn't going to lead us to freedom. So what else does emergence teach us? What are some other take-homes? We learned that large-scale phenomena can be independent of the constituents. Okay, so for example, both of these crystals are hard, but it's not because one's made of silicon and one's made of bismuth. There's some larger scale phenomenon going on, and it's independent of the microscopic constituents, which helps you understand that it's not because of the microscopic constituents. This isn't hard because it's silicon, and this isn't hard because it's bismuth. They're both hard because they're crystals. So large-scale phenomena can be independent of constituents. And this leads us into an idea that would be beyond emergence. Sometimes we find large-scale structure that's emergent, okay, like the wave, for example, or like wetness in water. Sometimes we find large-scale structure that's not even emergent. I would call it more transcendent, right? So I've got here some houses, you know, and if you were to look at the floor plan of my house, and you come into the foyer and you would see, well, there's the living room, and isn't it interesting that the living room flows into the kitchen and so forth. You wouldn't walk in and say, oh, that's a lovely floor plan. It's because you used bricks to build the house. Well, that's not right, right? The floor plan didn't actually emerge out of the building material. The floor plan would have worked whether we used bricks or wood or stone. And that's an example of large scale organizations that are actually transcendent. They're imposed onto the physical system. That can also happen. Things can also happen beyond emergent. So that leads us back to this big idea of, why is the Mona Lisa smiling? Why am I smiling? I hope you're smiling. I can't see you at the moment, but I hope you're enjoying this lecture. And why is it that we're able to have those kind of things? Are we only the sum of our atoms, or is it possible that that the light in our eyes is due to something more than our atoms? There's something more there than can be explained just by determinism and just by physics. So let me leave you with this idea that reductive determinism, it does preclude free will because things are just following, physical law lockstep. But to go from that and to make the leap, as we sometimes see our materialist friends and colleagues doing, to make the leap that therefore free will doesn't exist in the way that Susan Blackmore did, right? Susan Blackmore said, well, reductive determinism precludes free will, therefore I don't have free will. That's a big therefore, but I think it's a fruitful avenue of discussion with our friends and colleagues. I have certainly found it fruitful in discussing with my colleagues, that look, if all there is physics and physical law, you don't have any freedom. You're not really making choices. Are you okay with that? And that kind of is just a little bit to make people think along the lines of that there could be more. As we are confident as believers, there is more that the Lord has given us than that.